two 15-story boosters falling from space, executing a synchronized vertical landing over the Florida coastline. Reaching this precise moment required solving a massive physical logistics problem, orchestrating the violent ascent, separation, and recovery of three connected rocket cores simultaneously. The physical scale of the Falcon Heavy architecture reveals the scope of the challenge. The vehicle relies on two previously flown boosters attached directly to a central core. This vector graphic maps the structural attachment points between the cores. 27 engines firing create massive acoustic waves, transferring destructive vibrations from the outer boosters into the center stage. To survive these forces, the center core had to be a newly reinforced, custom-built stage. Marrying three rockets multiplies the potential points of catastrophic failure exponentially compared to a single-core vehicle. At Launch Complex 39A, the ignition of all 27 engines generated more than 5 million pounds of thrust. This cross-section shows the engine bells during ascent. The outer 18 engines operate at maximum output, while the central 9 immediately throttle down to conserve fuel. The vehicle rapidly climbs through the lower atmosphere, approaching maximum dynamic pressure, known as max Q. During this phase, extreme aerodynamic loading threatens to snap the structural attachments and rip the side boosters off. Pushing through that barrier intact validated the tri-core design. The years of computer modeling held up against the physical reality of atmospheric resistance. At 2 minutes and 33 seconds into the flight, the outer engines cut off, and the side boosters physically detach from the center vehicle. Shedding that massive dead weight allows the center core to immediately throttle its 9 engines back up to full power. The two free-falling side boosters immediately flip their orientation, executing a boost-back burn to reverse their trajectory toward the Florida coast. To steer through the thinning air, the boosters deploy specialized titanium grid fins. They act as aerodynamic control surfaces, guiding the cylinders with tight precision. Approaching the ground, they execute a staggered reignition of their engines, rapidly decelerating for a simultaneous touchdown at landing zones 1 and 2. Executing this synchronized return proved that recovering multiple boosters on a single flight was logistically feasible, establishing the economic basis for heavy lift reuse. 30 seconds later, the center core completes its burn and separates from the second stage. Because it carried the payload higher and faster than the side boosters, the center core faced a much hotter re-entry profile, aiming for an autonomous drone ship out in the Atlantic Ocean. This engine schematic shows the depletion of TETEB ignition fluid. Without it, the outer 2 engines failed to relight. Missing required thrust, the core impacted the ocean at 300 miles per hour, missing the drone ship by 100 meters and damaging its thrusters. The hardware was lost, but attributing the crash to a simple fluid shortage meant the core aerodynamics and guidance physics were sound, confirming the heavy lift architecture was structurally safe. Out in the vacuum of space, the second stage ignites and sheds its protective payload fairing. Mounted to the custom adapter was an unconventional payload, a 2008 Tesla Roadster, driven by a spacesuit-clad mannequin named Starman. The upper stage and its payload then entered a grueling 6-hour orbital coast phase, a trajectory designed to drag the vehicle directly through the Earth's highly radioactive Van Allen belts. This radiation exposure was a necessary requirement. The military and scientific communities needed proof that the upper stage avionics and propellants could survive deep space environments and still reliably reignite. Surviving this intense radiation coast certified the Falcon Heavy upper stage to carry the nation's most complex and expensive orbital assets. After 6 hours of absorbing radiation, the upper stage engine successfully executed its final restart. This vector map charts the payload's final trajectory. It bypassed Mars' orbit, entering an elliptical heliocentric path swinging outward past the red planet. Without active propulsion, the payload is permanently locked into this sun-orbiting path for millions of years. Conquering the mechanics of 27 engine synchronization and demonstrating multi-core recovery resulted in the world's most capable operational rocket. By proving the heavy lift vehicle was viable, aerospace engineers closed this developmental chapter and redirected national resources toward the next milestone, returning crewed human spaceflight to American soil.